identity matrix is a square matrix that consists of ones across the leading diagonal and everywhere else zeros. So in the first case, we've got a 2 by 2 matrix. You can see it's a 1, 0, 0, 1. So the leading diagonal is here from the top left-hand side to the bottom right. There we have ones, everything else zeros. Here's the identity matrix for a 4 by 4. And you can see once again from the top left through the diagonal to the bottom right, we've got ones, everywhere else zeros. Now the big idea behind an identity matrix is that it behaves like the number 1 does in the number system. So for example, if we took the number 5 and we multiplied by 1, would return number 5. And the same thing applies for identity matrices with the multiplication of matrices. Let's look at this first example where matrix A is defined as being 3, 10, 2, 5. If I take that matrix A and I multiply by the identity, and so given that this is a 2 by 2 matrix, the identity matrix for a 2 by 2 is 1, 0, 0, 1. So if I now have that matrix A, I multiply by the identity, you can see that the result is 3, 10, 2, 5, which of course is matrix A. Now we can do this by hand, or we can just simply do that using our CAS to come up with that proof that this matrix A multiplied by the identity returns matrix A. Let's now take a look at changing the order. So if we take the identity matrix 1, 0, 0, 1, multiplied by matrix A 3, 10, 2, 5, you can see the result is matrix A. So what we've found there is that matrix A multiplied by the identity is equivalent to the identity multiplied by matrix A, and that is equal to matrix A. So what's the effect of either pre-multiplying by the identity or just multiplying after by the identity? Is basically no effect. We'll return matrix A. And that's the same idea as what I spoke about at the start there. If we have number 5 and we multiply it by 1, then we just return number 5. So matrix A multiplied by the identity just returns matrix A. And the order for that is not important. And that's shown here. Okay, inverse matrices. First of all, let's consider the inverse of number 5. The inverse of number 5 is 1/5. If I take 5 and multiply by its inverse, I'll return number 1. If I start with 1/5, the inverse of 1/5 is 5. So if I have 1/5 and I multiply by its inverse, again, I'll return 1. The same thing applies for matrices. So if I have matrix A and I multiply by its inverse matrix, and I can write that as being capital A written as to the power of -1, then I'll return the identity matrix. Remember at the very beginning I said that the identity matrix in matrices is similar to the number 1 in our number system. You'll also see if I start off with the inverse of matrix A and multiply it by matrix A, I'll also return the identity. Let's take a look at this example too. We need to show that this first matrix and the second matrix are inverses. So what should happen is if I multiply this first by the second, I should return the identity matrix if they are inverses. And that's just based on this bit of knowledge here in the blue box. So let's do it. 3, 7, 2, 5 being multiplied by the matrix 5, -7, -2, 3. Of course, I can do that by hand, I can do it by CAS, but you can see the result is 1, 0, 0, 1, and that is the identity matrix, which is of the dimensions 2 by 2. We also need to double check it. So whilst we've got that first matrix multiplied by the second, let's test it out by taking the second matrix and then multiplying that by the first. So we'll change the order here. So you can see I've changed the order, and then when we calculate that, again, the identity matrix is the result. So we've verified that those two matrices are inverses. So whilst that proves that they are inverses, how is it that we go and calculate what the inverse matrix is? And there's a special rule for this. If I've got matrix A and it's of dimension 2 by 2, where the elements are A, B, C, D, then the determinant is simply going to be the product of that diagonal, so A times D, minus the product of this diagonal, C times B. And that there is what we refer to as being the determinant. The inverse of matrix A is this, 1 over the determinant being multiplied by this matrix here. So what happens is that I look at my original matrix and I change that order, so the D will move to where the A position is and the A will move to where the D is. And then along this diagonal, I'll change the sign that's in front of the C and in front of the B. So you can see the A and D here have changed, and you can see I take the negatives along this diagonal. So along this diagonal, we just interchange them or flip them, and then here we change the sign. Out the front, I've got 1 over the determinant, and of course the determinant is AD minus CB or BC. And here's our steps summarised in the blue box. So calculate the det or determinant, AD minus BC, multiplied by 1 over the determinant, and then in the matrix, swap over A and D, and then change the signs of the other diagonal, BC. So let's look at the example. For the first case, for A, I need to work out the determinant to begin with. So the det of A is simply 6 times 3 minus 8 times 2. And you can see that the determinant is 2. The inverse, so I write that as being capital A to that power of negative 1. So it's 1 over the determinant. The determinant's been calculated in step 1. And then what I need to do is interchange those two. So put the 3 where the 6 is and the 6 where the 3 is. You can see I've done that here. And then along this diagonal, I just need to put a negative sign out the front. Or just change the sign. So that will become negative 8 and this will become negative 2. You can see that's the case as well. So we've got this fraction out the front. So I can now multiply everything that's inside that matrix by what's outside. So we can see what we've got there, 3 on 2, negative 2 on 2, negative 8 on 2, 6 on 2. And of course, in lots of those cases, the fractions can simplify. So negative 8 on 2 becomes just negative 4, negative 2 on 2 becomes negative 1, 6 on 2 becomes 3, and then 3 on 2 doesn't change. Same idea for B. So here's matrix B, it's 8, 2, 8, 2. Calculate its determinant. So the determinant of this will be 8 times 2 minus 8 times 2, and that gives us a result of 0. Now, whilst that the determinant is equal to 0, the inverse for this will not exist, and it's pretty simple why. The proof of it is that the determinant is equal to 0, but why is it that we can't evaluate what the inverse is? Remember, the inverse is simply 1 over the determinant being multiplied by this rearrangement here. So if you've got a 1 there and a 0 here, you're asking yourself how many times does 0 fit into 1? And you can't find an answer for that. So if you can't evaluate what that fraction is, if this fraction is undefined, then if we multiply that undefined figure through this matrix here, the whole lot's still going to be undefined. So therefore, the inverse of that matrix would not exist. And that's the case here. So matrix B does not have an inverse. The reason being that the determinant is equal to 0, and logically it makes sense because we know that the inverse is 1 over the determinant multiplied by that rearrangement. And 1 over 0 is undefined, so therefore the inverse does not exist. All right, example 4. We've got a matrix and all the elements are known except for the bottom left-hand corner where we've got an x. We know the determinant is equal to 21 and we have to work out what the value of x is. So the determinant of this matrix is going to be 5 times 3 minus x times negative 3. And so I've got my workings in there for the determinant. I also know from the question that it's equal to 21, so the 21 goes here. Tidying things up, I have 21 equals 15 plus 3x. Now to solve for x, all I have to do is use solve function on my CAS. So menu, algebra, solve, put in this line here, comma x, and you'll see that the solution for this is x equaling 2. Okay, B. For matrix A, we've got 2, 3, x negative 4. What is the value of x for which that matrix A is equal to its inverse. So it's a bit of a multi-step kind of a question. To begin with, we're going to work out what what the inverse of matrix A is in terms of x. So first job, let's work out the determinant. So it's going to be 2 times -4 minus x times 3. So I have the determinant equaling -8 take away 3x. Its inverse will be 1 over the determinant. And then I rearrange the values inside the matrix. So -4 will go to where the 2 is, and the 2 will go to where the -4 is. Then across this diagonal, I'll change that to a -x and a -3, which I've done here. My next move is to multiply that 1 over the determinant through the matrix. So you can see that -4 multiplied by 1 over -8 minus 3x becomes this. And I do that for all of the elements. Now let's go and take a look at what the condition is here in the question. We want matrix A to equal its inverse. So there's matrix A, there's its inverse. Matrix A is this matrix. Its inverse is here. And so if they are equal, then all corresponding elements in the matrices will be equal as well. So 2 will be equal to this, 3 will be equal to that, x will be equal to this, and -4 will be equal to that. So I'm just going to equate row 1, column 1 of each matrix. So 2 will equal -4 over -8 minus 3x. And of course, I just use solve on my CAS to establish that x is equal to -2. So a few little steps in that one, but it all relies on working out the determinant, its inverse, then equating matrix A to its inverse, and then equating corresponding elements, solving for x. C is quite tricky, but let's work through it. Okay, show that if A and B are both square matrices and A plus B is defined, then the inverse of A multiplied by B plus A to the power of 4 is defined also. So let's start. If we've got matrix A and B are both square matrices, so this is this bit of information here from the question, then I can write that A is equal to an m by m matrix, m number of rows by m number of columns. Likewise, if B is also a square matrix, then I can write that as being n number of rows by n number of columns. So you can see there the rows and columns in each of these matrices are the same. Second bit of information, A plus B is defined. In order for us to add matrices together or subtract matrices together, they need to be exactly the same dimension. So the dimension of matrix A must equal the dimensions of matrix B. So A and B is defined, therefore M and N must be of the same order. That is that M is equal to N. So let's just go with that we'll use M's. So instead of N's, M's. So we now know that matrix A is an m by m matrix and matrix B is an m by m matrix. The other bit of information that's missing here is A to the power of 4. Okay, so if you take any matrix and you raise it to a power, firstly, it must be a square matrix, and secondly, the resultant matrix or the answer for that will be of the same dimension. So A to the power of 4, given that A is an m by m matrix, then A to the power of 4 will also be an m by m matrix. So A is an m by m matrix, its inverse will be of the same dimension, so that's an m by m matrix, and A to the power of 4 is an m by m matrix. So if we look at our expression, then I've got the inverse, that's an m by m, being multiplied by a B, and that's also an m by m, and then A to the power of 4, that's what we're adding to it, is also an m by m matrix. If we take the inverse matrix and multiply it by that B matrix, then you can see that it's possible to do that multiplication because the two inners are the same. Furthermore, the result will be an m by m matrix, the two outers. So you can see now that taking into account of this, I've got an n by n matrix. I'm adding to it a to the power of 4, which we've already established as an n by n matrix. Now, because we're adding two matrices of exactly the same dimension, it is possible, and the result of it will also be an n by n matrix. So by going through all of this logic, what we've proven is that under these conditions, this expression here is defined. Here we have to use our CAS calculator to work out the determinant and the inverse of any given matrix. Now, of course, with 2 by 2 matrices, you can do it all by hand, but we have no technique to do it for a 3 by 3 matrix. This isn't a bad approach, what's shown here in the notes, but rather than defining the matrix, I'm going to do it a little bit differently and just use copy and paste. So watch what I do with the CAS. So I've just got a calculator page. So I'm going to bring in a matrix to this. So if I just hit the template button, and you can see I've got all my presets. I've got a 2 by 2, a 1 by 2, a 2 by 1, and then here it's showing me a 3 by 3, but I can make this whatever dimensions I like. So I'm going to go with a 3 by 3 matrix. So just hang in there whilst I put all the data in. So I'm just going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, I'm just going to go enter. So there's the matrix, it's entered and it's stored. If I want to bring up the determinant or calculate the determinant of that matrix, then all I need to do is go back and select the matrix that I want to take the determinant of and go Control C, so it's copied. And then move my cursor down, go menu, and then I want to go to matrix and vectors, and then go determinant. So that brings up that det, and then I'm going to place inside the brackets the actual matrix. So I'm now going to go Control V. So it'll take the determinant of that matrix, hit enter, and you can see the result of that is 0. Now, of course, what we'd expect here is that if we take the inverse of that, because of the determinant is equal to 0, I should have something that's undefined. So to calculate the inverse of that particular matrix, I can just go Control V, so that'll place in that original matrix. And then what I'm going to do is raise it to the power of -1. So use this little coordinate symbol over here on the left-hand side. Just means to the power of -1. And would expect this to be undefined given that the determinant is equal to 0. And I cannot find a solution for that. That there just means it's undefined. Now, if I just go and change that a little bit, so I'll go Control V, and I'll just change the matrix around a little bit. 9, and I'll make this a 22. And now hit enter. You can see there's my matrix. If I work out the determinant of this, so I'll copy that. Whoops. Control C. And now go down and again go menu, matrix and vector, determinant, and paste it in, hit enter. You can see now I've got a number that's different than 0, so -549. So in theory, I should be able to work out the inverse of this matrix. So I'll just go Control V to paste that matrix again, and once more raise it to the power of -1. Hit enter, and I should get a result. And you can see there's my inverse matrix. Now what we also know is that we really should be able to take this inverse and multiply it by the original matrix, which is further up, and I should get myself the identity matrix, and you can of course verify that and test that out. But I won't.